Hi, this is Lee Vishloff, the principal of Technose Services Inc. Technose is in the business of helping you advance your products from early stage development models to customer and factory ready designs. Tech projects fail for simple reasons. One of these reasons is poor testing, so today we're going to discuss how we know when our products actually work. Here's our outline. First, we'll look at some of the methods of verification. There's more than just testing. The V model, which is a way of looking at our product development from beginning to the end. The 7 things that need to be correct in order to get a pass of a test. The motivation of the testers, and finally a summary. So there are 5 ways typically used to show that something works. When we're proving that our system is up to spec, we will be using one of these. An item verified by demonstration can be done without test equipment, and an example might be, verify that the control switch turns on the light. So if your house wired, that's pretty well what you're going to do. It's going to be done by demonstration. An inspection item are often also included in a test plan. And an example might be specification says that the unit should contain no fans. So this is a fairly common requirement for industrial grade outside wireless equipment. There shouldn't be any fans in it. And it's easily verified by using one's eyes and ears. The analysis can be a bit of a weaker form of verification, as there are always assumptions about the environment included in the analysis. The classic product development example is mean time between failure, MTBF. This is almost always done via analysis, and because there is really no or very limited field data when a product is being tested, especially if it's the first of its kind. And so we always do some sort of calculation to estimate how long we think this product will work between failures. Certification is often associated with your product's inputs. For example, if you buy wireless modules that go into your product, they will have a stamp on them that says they're CE FCC compliant. They will have documentation that tells you they've been approved for a variety of vendors' networks, and you take that as part of the verification that your system is going to work. And the most stringent and difficult of all of these methods is, of course, the actual test. Tests typically require specialized test equipment. They often have complex testing environments, and we have to simulate or synthesize situations in the lab that we might experience only rarely in real life. And we're usually looking for numerical results. For the rest of our talk, we should just assume that we are talking about this kind of verification, the test. So the V model is, I think, fairly well known. This particular drawing has been modified and comes from the INCO System Engineering Handbook, 2011 version. And we start at the top with a vague idea. We have a commercial requirement, and then it turns into a system design. And often the system design deals with higher level concepts and subsystems in their entirety, and provide some view overall of what it is they're to do without getting into the microscopic details of how each of the sub-elements is going to work. Now, we will then go down the decomposition and definition side of the V, and so we will have subsystems and systems of various software modules and whatnot that will comprise our overall system. And then we get right down to the unit level, where you're looking at individual code blocks or individual printed circuit boards or ASICs or whatever it is that you're making. Then what will happen is that we will test the individual units, and then we will integrate them and work our way back up the chain on the other side until we have a completed product. Now, at the top of the model, we use what's called black box testing. So we write test plans and verification strategies that are really taking the customer's view of how the system works. At the bottom, we do what's called white box testing. And the white box means that you're allowed to look inside and really understand how the device works. So if you had some sort of clock recovery circuit, for example, you might have a specification that says the clock recovery circuit will acquire data at this noise level within so many milliseconds or microseconds or whatever is appropriate for the device you're using. But that is not really a customer type of specification. The customer spec would be, we want to turn the switch on and see that the system is operational within 10 seconds or something. So this is just one way of looking at a model. It does provide us a nice structure to think about how we're going to do our testing. Because as you write your specifications and you work your way down the left-hand side of the V, as you write the specs, you should think about how it is you're going to verify that spec is being met. Is it by inspection? Is it by test? Is it by some other means, analysis? And it not only helps you write your test plans later if you flag it as to how we're going to verify it, but it also helps you better understand the feature and the requirement that you're actually defining at the time, because how you test it gives you some idea of how you think you want the customer to perceive it. So now there's a bunch of things that need to work in order to get a pass. When a test fails, we don't actually know for sure that it is the product design that is defective. Now our thinking is mainly focused on item 2. We're focused on the design of the product and we're trying to prove it. But there's 6 other things going on there as well that need to be correct in order for the system to work and pass our test. First off, the designer has to have correctly interpreted the spec. So if the spec was vague in some way, that leads it to some vagary. Item 2, of course, is totally focused on our normal interpretation of testing and what it's about, which is proving that we have a design that works as we would like it to work. Now, in between the design and actually getting it into the tester's hands, there's this building process. Either a software build or a printed circuit board has to be assembled, or subunits need to be integrated in some way. And there's no guarantee that if different people are doing the building than who did the designing, that you'll get exactly what it is that you thought. Or even if you're doing it yourself, you might make a mistake. You might get the wrong component in the wrong spot in your printed circuit board, or you might have used the wrong version of a particular software module. If there's some issues with your configuration management or your build tools. So there's a variety of things that can happen so that your product is actually built slightly differently than what it was that you designed and what you were expecting. Then we need to have valid test plans. People who write the testing plans tend to look at it from hopefully an outside perspective, not the inside, but there may be things that they do in order to produce certain situations that are not valid when we look at the actual implementation that we've chosen. And then the lab system, test system, needs to be working properly. And there's a lot of very expensive, complicated test equipment in the world. And if you're testing data networking equipment or some new wireless equipment, you often have a lot of gear, and you need to create some sort of synthetic environment that emulates certain conditions of the real world. Because while we always need to test over a live system before we release to customers as final validation, it's rarely good enough to just do that, because we don't have control over the operating condition of that particular network, whether it's a radio network and it's subject to noise and interference and propagation vagaries, or it's a data networking system and it's subject to flash crowds and router failures and flaps and all the things that can happen. And usually a network in its day-to-day working condition is not that heavily loaded. And when you're testing your own product, you want to be able to test the various corners where things can get really ugly. So if you just run on live networks, you run the risk that you have a false sense of comfort as to your design stability and operation. And then point 6, the tester does need to execute the test plan correctly, and last, the actual unit does need to be working properly. You can have stuff designed properly, built properly, and tested properly, and it can still be defective, because sometimes new products, new new parts come from the factory. They're not exactly within tolerance or something like, something that you are relying on to make this design work. But when all 7 of those things are working, we get ourselves a pass. So when you get a fail, think about all of those things as possible causes. Now we need to think a little bit about the tester's motivation. The purpose of all this activity, of course, is to get a product in the customer's hands that the customer will be happy with, one that works well. And ironically, the best way to reach this point is to have a tester who is actually trying to prove the opposite, that the design is faulty and that it doesn't work properly. When the tester can no longer find faults, or the faults that are found are deemed to be acceptable at this particular point in time, then of course we're ready to ship. If you're the designer or the coder, or somebody who's involved in the intimate details of the product, you know it very well, and there's a tendency for people to focus on the weakness that they know about, or things they worry about, or things they struggled with in order to make the design work, rather than taking a customer-oriented black box perspective. And of course there are pressures on the people who do the design to get on and move to the next particular task on their plate. So of course they want these things to be working and out of the way. So no matter how small your company is, do not test your own designs. As a minimum, do a swap with another designer, and you can take your time. You can swap between each other as to when you test and when you code or design. So in summary, there's really 3 things you need to think about. You need to plan your verification method for every specification that you write down and every feature, and know how you're going to prove that it works. To pass a test, you've got 7 things that need to be right. So think about that when you're designing your test plans. How will I know whether it's the unit that's failed or my test environment that's failed? And then you need to test with a mind to proving that the system is broken, not a mind to proving that it is working. And if you do those things, you will get your product out well tested, and you will have many happy customers. Thanks for listening.